Welcome to lecture 4.7, Face Portraits with Repeated Eigenvalues. Okay, so here's our first example. Consider the following homogeneous system, x prime equals a times x. So let's compute the eigenvalues and eigenvectors. So that's this determinant, negative 1 minus lambda, 0, 0, negative 1 minus lambda. And so this is 1 plus lambda squared equals 0, so it's easy to see that lambda 1 and lambda 2 are both negative 1, so we have a repeated eigenvalue. This is a case where we're going to have more than one eigenvector, and let's check. So a minus lambda I is a plus I, so times v equals 0, we need to solve for v. So that's so a plus lambda I is 0, 0, 0, 0. Actually, I should make that matrix, not the determinant, times x1, x2 equals 0, 0. So every single vector, x1 and x2, satisfies, every x1, x2 satisfies this. So we have every vector is an eigenvector. Now we don't actually need this. All we need are two vectors. So we need to find an x1 and an x2 to get the general solution. So let's just pick two. Let's take v1 to be 1, 0, and let's take v2 to be 0, 1, because why would we want to pick vectors that are harder than we need? And now the general solution is x of t equals c1 x1 of t plus c2 x2 of t, which is c1 e to the negative t 0, 1 plus c2 e to the negative t 0, 1. And if you want to, you can actually write this as, combine this into a single vector. You can write this as c1 e to the negative t and c2 e to the negative t. Now one thing I should mention is that we could have solved this system the old way. Now this system, it's technically a system, but it's something that we don't need our matrix analysis tricks for. So this is really just x1 prime equals negative x1 and x2 prime equals negative x2. This is something that we knew how to do very early on. And we knew that x1 of t equals c1 e to the negative t and x2 of t equals c2 e to the negative t. And that's exactly what we got down here. Okay, so let's plot this. Let's do the phase portrait. So let's suppose, well, how do I want to arrange this? So let's plot this, and let's say that x, our initial point, the phase portrait is some, well, if you plug in 0 into here, x of 0, you get c1, c2. So let's just call our initial point c1 and c2. So here, this is going to be our phase portrait. This is x1, this is x2, and let's suppose that our initial point is right here, and this is c1, c2. So then, note that the slope x2 of t over x1 of t, by x2 I mean this x2 and this x1, there's no vector involved here. This thing is just c2 over c1. This ratio is c2 over c1. So this curve at any point in time, the slope, or this thing lies on the line of slope C2 over C1. So that means that this line going through the origin, for any point in time, x2 over x1, the rise over run, is on this line. So if we start here, we're going to end up on this line. And also because, also the limit as t goes to infinity of x of t, or x of t, which is this, which is c1 e to the minus t, c2 e to the minus t. This is 0, 0. So that means that if we start here at this point, we're going to be diving into the origin like that. If we start at this point, at a different starting point, we're going to be diving into the origin like that. So no matter where we start, we're going to be, but I can draw that better. So no matter where we start, we're going to be going into the origin at exponential speed, because the speed is, this describes our path. So the phase portrait looks like a star like this, and recall that we actually saw this, or we discussed this a couple lectures ago when we were looking at phase portraits when the eigenvalues were real. And we, at the very end of the lecture, I said, well, what if the eigenvalues are really close to each other? Remember, when they're different from each other, we get this bend in the curves. But if they're really close, then the bend is almost nothing. And in the limit, we get where there is no bend, which is something like this. So we can also plot the component plots. So that's just plotting x1, or that's plotting x1 and x2 versus t. So this is my x1 and this is x2. So, and we know what these things look like. These are exponential functions that decay to 0 or limit to 0. So this is the phase portrait. Phase portrait. And then these over here, this is the component plot. And this is what we did last lecture as well when they were complex valued functions, or I guess complex exponentials I should say, and we had sines and cosines. So what I'm plotting here are I'm plotting I'm plotting x1 of t and x2 of t for various values of c1 and c2, which are going to be the y-intercept. So let me call this xi of t. That's the y-axis. Okay. So our next example is the following homogeneous system: x prime equals a times x. I think we may have actually found the eigenvalues and eigenvector of this matrix before a few lectures ago, but it doesn't take long to do it again, and it's good practice. So the determinant of a minus lambda I in this case is going to be negative 1 minus lambda, negative 1, 1, and negative 3 minus lambda. So if we multiply this times this, we can pull out a negative 1 from each of these, and they will multiply together to be 1, so we can write this as 1 plus lambda times 3 plus lambda plus 1, and that's lambda squared plus 4 lambda plus 4, which is 0, and so this is going to have roots lambda 1 equals lambda 2 equals negative 2. Okay, so to find the eigenvectors, we take a minus lambda I, which is a plus 2I, times v, so that's going to be negative 1 minus negative 2 is positive 1, right? Yeah, so I should probably make that positive 1. Positive 1, negative 1, positive 1, negative 1. Actually, I should make that a matrix and not a determinant. Times x1, x2 equals 0, 0. So we have that x1 minus x2 equals 0. So we get that x1 equals x2. So v1 is 1, 1. So this is an eigenvector, and it's the only one that we have. So we have one solution, and that's x1 of t equals e to the negative 2t times 1, 1. So the thing is that this is one solution, but we know the general solution. So the general solution is x of t. It has to be c1 x1 of t plus c2 x2 of t. And we know what this is, but somehow we have to cook up with a second solution so we can complete our general solution. Okay, so to summarize, we have one solution and we need one more. So how do we find the second solution? So it may seem a little out of left field now, but this will always work. So assume that the second solution, so what's tempting to do is to just take your first solution and stick a t in front of it, right? That's what worked for first and second order equations. We did not have systems. Now put a t in front, and that's not going to quite work, but something close to it works. So we're going to assume that x2 of t is t e to the minus 2t times v plus e to the minus 2t times w. So we're going to assume that the solution looks something like this, and we're going to solve for v and w. And that is always going to work. Okay, so how do we do this? Well, like usual, we take what we're assuming is the solution, and we need to plug it back into x prime equals ax. So we take our solution, plug it back into here, and figure out and solve for the unknowns. In this case, it's going to be v and w. Okay, so let's take the left-hand side. So we got to plug this back into the left-hand side and the right-hand side. So the left-hand side, this is going to be x2 prime, and that's going to be, so now we have to take the derivative of this. Now this is just as a constant vector. This is, think of it like 1, 2, or 2, 3. There's no t's in here. This is what we have to take the derivative of, this product, and then of this. So we do this using the product rule. So the derivative of, so in other words, we got to take the derivative of that and the derivative of that. So the derivative of the first thing is negative 2e to the minus 2t times t, let me stick the t right in there, times v. And then plus the derivative of t, which is 1 e to the negative 2t times v. And then the derivative of this guy is just pull out the negative 2. And we get minus 2 e to the minus 2t times w. So that's the left-hand side. And now the right-hand side of this. So let's take x2 and let's plug it into the right-hand side, a times x. So that's going to be a times x2, which is a times t e to the minus 2t times v plus e to the minus 2t times w. So what I have to do is I have to set the left-hand side, x2 prime, equal to the right-hand side, this thing. So I got to set this equal to that. So let's equate terms. So I have to set equal. So notice that all of the, okay, so if I multiply this out, I get at times, oh, I have two terms here, but every term either has t times e to the negative 2t in it, or it has just like this, e to the negative 2t in it. So let's write this down. Let's equate coefficients which are really vectors, because coefficients might have a v or a w in it. So equate coefficients of t e to the minus 2t and just e to the minus 2t. So, okay, so how many e to the, let's see, t times e to the minus 2t's do we have? So on the left-hand side, we have negative 2 times v, right? So we have negative 2 times v. And that's it. These two terms don't have a t in it. And down here on the right-hand side, over here, we have a times this times v. So set that equal to a times v. You see what I'm doing? I'm saying if this term, or if this has to be equal to that, then that term better be equal to that term. And similarly, the coefficient e to the minus 2t that doesn't have a t in it, we have one of those here, and we have one of those there. And so let's write that out. So that's v minus 2w. So this is how many e to the minus 2t's we have in the left-hand side, and that better be equal to a times this term over here. So that better be equal to a times w, because this is how many e to the 2t's we have on the right-hand side, or in this equation. So recall that our goal is to solve for v and w. So we got to find a v that satisfies this and a w that satisfies this. So this should look familiar. A times v equals negative 2v. That is only going to happen if v is an eigenvector of a with eigenvalue negative 2. Now, are we guaranteed that a is necessarily going to have an eigenvector of negative 2? In general, no, but fortunately, in this case, it does. And in fact, this is always going to happen, that this first equation is always going to be the eigenvector equation. So right away, we can say v is, so v is an eigenvector, so v is 1, 1. It's an eigenvector. That works, and that's always going to work. And if you get something that doesn't make sense, like if this were negative 3, there would be no solution for v, because v is negative 3 is not an eigenvalue of this. So in that case, we have done something wrong. Okay, so this second equation, let's try to understand this now. I'm going to move the w's to one side of the equation. I'm going to write this as a w plus 2w equals v, which I'm going to write as 1, 1. And so now I can write this left-hand side, I can factor out the w, and I can write this as a plus 2I times w equals 1, 1. And now we know what a plus 2I is. It's this matrix plus 2I, so let's actually write that again. So a plus 2I is the matrix. So let's add 2 to this entry and add 2 to that entry. And we get 1, negative 1, 1, negative 1 times w, let's call that w1, w2, equals 1, 1. So now, what does this tell us? This is a system. This says that w1 minus w2 equals 1. And it says that twice, so This is the system W1 equals W2 and W1, or not W1 equals W2, W1 minus W2 equals 1. Okay, so what does that say? So that means so we found W. Any W works as long as the difference as W1 minus W2 is 1. So this could be 1, 0, this could be 2, 1, it could be 3, 1, or so forth. So what this says is, see how I want to write this. So that says that W is, so whatever the heck W2 is, W1 is 1 more. So for any value of C, this works for W. So there's a whole family of solutions that could work for W. But we only need one of them. So let's pick the easiest possible one. Let's let C be 0. So let's choose W to be 1, 0. Because I like things that have a lot of zeros in them. So now we're done. Now we have our second solution. We know, so remember we were trying to find a second solution x2, and we guessed that it was of this form. And all we had to do was solve for v and solve for w. And so we said v has to be an eigenvector, so let's pick 1, 1 to make things easy. And w, given that choice of v, w can be anything like this, so 1, 0 certainly works. So now, let's hold space here, so x2 of t equals t times e to the minus 2t times 1, 1, that's my v, plus e to the minus 2t times 1, 0. So that is our second solution. Let me box that in red so we can see it. And now we have the general solution. Let's write it up here. The general solution is x of t equals c1 x1 of t plus c2 x2 of t. Recall that here's our x1. So I'm going to write this as c1 times e to the minus 2t times 1, 1 plus c2 e to the minus 2t. I'm going to factor out an e to the minus 2t from both of these. So c2 e to the minus 2t times, and now what's left? We have t times 1, 1 plus 1, 0. T times 1, 1 plus 1, 0. And if you take a more advanced linear algebra course, probably at Clemson it'll be a graduate course, you'll learn that this family of W, these things are called generalized eigenvectors. So yes, those things do exist. So here is our general solution. Let me box that in red as well. So this was the last and final case of solving a system of equations based on the eigenvalues and eigenvectors, and it was the most complicated one, is when you have a repeated root. And in general, throughout the class, you've seen that is the problem case. When there's a repeated root, things get harder, and this was no exception. Okay, so the last thing we'll do is sketch the phase portrait of this system. So we have x prime equals a times x, and let me rewrite this solution as, I'm just going to multiply out the terms, that's all I'm doing here. So here's the first term. Second term is different because we have a t in it. It's t e to the minus 2t. E to the minus t. And that will actually be important, as we'll see shortly. Then the last term is c2 e to the minus 2t times 1, 0. So what I want you to notice is that of these three terms, so as t goes to infinity, all of these three terms are going to go to infinity, are going to go to 0, but this term is going to go slower because of the t. So as t gets larger and larger, these things get small, but this t prevents this thing from going to 0 as fast as the others. So let me say that. So this goes to 0 faster, and this term goes to 0 slower, and this one goes to 0 faster. And again, because this t, as t gets larger, the exponential gets smaller, but this t slows it down. So let me say that let me summarize this. So the t e to the minus 2t term, let's put a 1 in here. This term, I'm going to say this dominates the limit as t goes to infinity. Okay, so let's take the other limit. Let's suppose t goes to negative infinity. So in that case, this thing is large in magnitude. I'm not worried about the sign S-I-G-N because we don't know about the sign of this. But this thing is large in magnitude when t is I don't know if I want to say a smaller, large negative number. So as t becomes more and more negative, this thing gets larger and larger, this thing gets larger and larger, this thing gets even larger and larger, because not only is this thing huge, but the t makes it even bigger, as this is big in magnitude. So not only does this term dominate, I forgot my end quotes, not only does it dominate the limit as t goes to infinity, but it dominates the limit as t goes to negative infinity as well. So I'm going to say as t goes to plus and minus infinity. So what this means is that forwards in time and backwards in time, solutions become more and more parallel to this vector. So both forward, how do I want to say that? So solutions become, let me write a little better than that, become more and more parallel. These are things we could formalize if we want to talk about limits, but we're not going to. Limits and asymptotics, it's a little bit beyond the scope of this class. So more and more parallel to v equals 1, 1, both forward and backwards in time. Okay, so what does that mean? Let me fix that again. Forward in time. So what does that mean in terms of the face portrait? So let me sketch the face portrait is going to look like. So this is going to be x1 and this is going to be x2. Now let me sketch this eigenvector. This is 1, 1. So I'm going to sketch the eigenvector line as we did before. And we don't know much so far. We know that any solution that starts on this line ends on this line. So let's make C2 equals 0. That kills off this complicated term. And then we just have this. And then we're back into what we had before. So we had a solution that starts in 1, 1, or starts somewhere in this line, and as t goes to infinity, this thing goes to 0, and the solution goes toward the origin. So solutions on this line, they get sucked in to the origin, something like this. But the question is, what happens off this line? So if we had another eigenvector line, we could sort of fill in the gaps, but we don't now. So we have some solution. What about the solution that goes through this point right there? What happens? Everything's going to approach the origin, but does it like this, or like this, or like this, or what happens? So whatever happens, as we go forward in time, the solution becomes parallel to, so it might do something like this. It might become, so as t gets bigger and bigger, the solution is becoming more and more parallel closer and closer to this line. And as we go backwards in time, the solution becomes more and more parallel as well. So it's not a proof, but it's believable that a spiral, something like, not really a spiral, something like this has that property that forward in time it never quite hits the origin, but it limits toward it. Forward in time, this line becomes more and more parallel to this x equals y line, and backwards in time it becomes parallel as well. So let me sketch what I'm saying here. So there's two possibilities, and we're not really sure which one is going to be which yet. So one possibility. Let me put these arrows in like this. One possibility is that these solution curves spiral like this. I mean, again, I haven't proven this, but at least it's believable. You can see these curves are both forward in time and backwards in time limiting toward this line, at least their slope is, that is. And then backwards, so we have things that look like this. So that's one possibility. The other possibility is the reflection about this. So instead of spiraling this way, we spiral that way. So let me draw that. So let's suppose we were to something like this. And then so curves that look like this. So the face portrait is going to look like one of these two things. Question is which one? So how do we figure this out? So it gets kind of messy near the origin. This thing twists around a lot, but let's go way out here. Let's go to the point, say 10, 0, or if you don't think that's big enough, 100, 0. So let's say this is the point 10, 0, and let's ask, what is the slope of the tangent? What's the tangent line, the tangent vector to this curve? Does it go off in that direction, into the northeast direction, or if we were in this case, it would go off to the southwest direction like this? So see what I'm saying? So this point, say the point is 10, 0, is our velocity vector, or our derivative, is that going to be, so this is x prime, is it going to be that, or is it going to be in this direction? And that's something we can find out rather easily. We just plug it back into here. So let's check. So x prime at the point 10, 0, how do we figure this out? Well, so the point 10, 0, that's the point x1, x2, i.e. at 10, 0. So don't forget that this is x1 and x2. So x prime at 10, 0 is, let's compute it, is a times 10, 0. And I don't care about what time that is. I just care about about the fact that it's 10, 0. So let's take negative 1, 1, 3, and let's compute. Let's multiply by 10, 0. If we do this, we get negative 10, and we get positive 10. So that vector, so 10, negative 10, if this is the xy plane, or the x1, x2 plane, 10, negative 10 is a vector that goes in that direction. So that tells us that we must have this situation rather than this situation. Notice if I had done, instead of 10, 0, if I had done 1, 0, it's not quite clear that we would escape this sort of twisting that we have close to the origin. So given that, we can, I guess I don't need to redraw it, but yeah, let's do it. So the face portrait is going to look like something like this. It's going to spiral this way. And that little trick of just seeing what the slope of the tangent vector was at some point where we know it's either going to be that direction or that direction, that would actually help us. In the previous lecture, remember when we had those ellipses and we didn't know which way they spiraled? With circles we could figure them out, but with ellipses not necessarily. The same trick works. Plug in plug in the easy point. Plug in, so let's suppose you have an ellipse. Let's go up here. Let's suppose that you know you have an ellipse in this direction. You don't know which way it spirals. Well, plug in 1, 0. Plug in this point right here. These things are all going to be, even though that's not 1, 0, these are all going to be concentric, so there's one of them that looks like it. And compute x prime and see, does it go in that direction or does it go in that direction? And if it's an entry with, say, 2 positive entries, then we know the ellipses must be spiraling in that direction. Otherwise, they have to be going in the opposite direction.